And so we'll do one more problem to kind of finish out this section, and I think this will lock in kind of everything that we've gone through so far. And there's more practice available. I'll do a few on the screen afterwards that you can try yourself. But this is probably one of the bigger ones that we can do. So we're going to take this number, 17 to the 23rd, and we want to find the last digit, right? Which was 5.3, if you recall the chapter before this, or rather the section before this, we were finding last digits. So you want to combine pretty much everything you've learned so far to be able to do this, right? So we look at this number, and obviously we want to know the last digit. We recall that the product, or the last digit of the product or sum of two numbers is the last digit of the products or the sums, right? So we look at this, and probably the first thing we want to do is kind of similar to what we were doing before, which is just we want to attack the base, right? We want to get the base lower to make the number more manageable, right? Because we saw that even with two numbers like 10 and 2, the difference when raised to powers is pretty massive, right? Because it scales so fast. Like 10 to the third compared to 2 to the third are orders of magnitudes different. And the same would, apply with 17 to the 23rd versus whatever number we can find that's congruent to the space. So we'll use mod 10 for this purpose. It's pretty good just for preserving the value of the last digit, so we're going to use that. So we'll do 17 mod 10, and that's congruent 17 minus 10, 7, congruent 7 mod 10. And recall that this will, congruency preserves behaviors and has it survive through powers. So instead of 17 to the 23rd, we can find the last digit, 7 to the 23rd. And then now we can't really do anything further with this because 7 mod 10 is the smallest non-negative integer. So now we're going to have to do some law of exponent stuff. So you might recall we did something similar to this. This number is definitely much easier to work with. This is what, 343. So we're good with this for now. We can kind of toss this aside and work on 7 to the 20. All right. We want to shrink this down. Well, recall again, law of exponents. This is just equal 7 squared. Or it's the 10th power. And again, all we care about is the last digit behavior. So this represents 49 to the 10th. And then in terms of the last digit, all we care about is the 9, right? The 10th. And then we know, I don't think I covered this, but in terms of the last digit, when we apply a power like this, right, the digit that's going to be used will alternate accordingly to whether or not the exponent is odd or even. And what I mean by that is if we do 9 times 9, that equals 81, so the last digit is 1, right? If we do 9 times 9 times 9, that's 81 times 9, which is 9. 80 times 9, 720. Excuse me. So it's 729, which is the last value of 9. So it'll alternate between these, because again, we're going to do for 9 times 9 times 9 times 9, 729 times 9, and we know that the last digit of that is going to be equal to 81, or 1. So accordingly, since this is a 10, the last digit of this is actually just going to be the even one, which is about the same as 9 squared, which is just 81, so it's a last digit of 1. So 7 to the 20, its last digit is 1. And then we're multiplying it by 7 to the 3rd, which we know just from offhand memorization of powers is equal to 343. So the last digit of 1 times the last digit of 3 equals a last digit of 3. And surprisingly, just from that, we're done. We know that because 7 to the 23rd is congruent to 17 to the 23rd when we do a mod of 10, excuse me. Since these two numbers are congruent, then they should have the same remainder and thus should have the same last digit of 3. And then lastly, before we go in this chapter, I just want to cover the cyclical behavior. You might have kind of seen it, and I kind of alluded to it, that implied the powers of it, but I didn't clearly define it. And there are, again, some pretty heavy notation proofs I could show you that you'll probably spend more time wrestling with than actually understanding the meaning of itself. So I think I'll kind of break it down like this. So the reason why with congruence things survive multiplication is, again, kind of based on last section 5.3, the last digit. So if we take numbers that are congruent, right? Like if we do 17 mod 10, right? That's congruent to what, 7 mod 10? I think, right? Yeah, because the cycles, by the way, just go plus or minus 10. So that's a pretty nice, easy way to cheat. So we could say that 27 mod 10 is congruent as well, right? Because 10 goes into 27, excuse me, 2 times, remainder of 7. We know this has a remainder of 7. So that means pretty easily this has a remainder of 7, obviously. All this means, this congruency means, is that these numbers behave the same, right? Because you can also think of it like this. Right? If we were to just take 17 itself, 17 in mod 10 behaves like 7 mod 10 because we just add 7 plus 10, right? It's kind of what I went over just now, right? When I said that you just subtract 10, you get 7. You see 7 mod 10. That's kind of the whole cyclical behavior. That's why when you raise something to a power, you raise it to, doesn't even matter, you raise it to some crazy high power, right? As long as you raise this to some crazy high power, they'll behave the same. They'll have the same remainder. Because if you multiply them by the same thing, these values in mod 10 still gonna have the same last digit, still gonna have the same remainder. And that's really as much as you need to understand regarding it. Again, there's some proofs, there's plenty of videos on YouTube going over the exact proofs in full mathematical language, but I wanted to focus on what it actually means and kind of the behavior you want to focus on. As long as you understand that that's all about cycles, wrapping around last digit behavior, and really just you want to stop thinking about numbers in terms of their values. Like the number 17 has a value of 17. You want to start thinking about the numbers in terms of their behavior and the properties they exhibit. When you start doing that, you start opening the door to some pretty interesting operations that could save you a lot of time, and honestly also some different modes of thinking that can expand your ability to understand and intuit problems that you haven't seen before.